In the last few segments, we discussed some facts and features about pure torsion of a shaft, right? So, if I would like to summarize, so we discussed the canonical situation like this: uniform cross section, T and T, and then we talked about the conditions basically, or assumptions. Under which or which generally are valid, the conditions or assumptions which are valid under pure torsion of an axisymmetric shaft. And then based on that, we defined the strain basically, gamma, and that was like, so if a line which was initially like that and finally it became like this, so this angle gamma we defined as the shear strain, and then based on, and then we discussed about its variation in fact over the radius, if when we move from the center to the circumference, how this gamma changes. And based on that, we also discussed about the stress. So stress tau, and we also discussed about how the state of stress exists. What is the state of stress that exists under such condition? And then we discussed about the distribution of this tau along the radius when we move, because it's an axisymmetric problem, so everything is axisymmetric. So no change happens with respect to theta. So whatever happens, whatever change happens, that happens along r. So tau, so I can explicitly write, so like this is gamma is a function of r, and tau is also a function of r, radius. And then based on that, we also derived the relationship between the applied torque with the stress field that develops. Okay, so the maximum shear stress that gets developed, and the geometric property of the section where we defined the polar moment of inertia. So all these things we did. So these are, in a way, we moved like this in sequence. And now the next discussion which we will have in this segment is about the angle of twist. That means if, so I'll say fifth point is like on angle of twist. Now we assumed earlier in all the things which we had developed up to this point, this angle phi, so this angle phi through which the whole shaft, means not the whole shaft, I'll say the maximum angle through which the shaft rotated, so that we will call the angle of twist. So that was assumed to be a given constant phi, though we also talked about how phi will vary with respect to length and radius, but for a given torque, length and a given shaft, we considered phi to be known, and then we discussed everything. And now our job is to find phi as a function of the torque that we apply. Okay, because that's a question which is very important, right? So like in the previous case, we said that what is the stress that's get developed when we apply a certain amount of torque to a uniform shaft. But another question which is equally important, and that is what is the angle of twist that gets developed under a torque of T. So we have to in fact get this dependence of the angle of twist on the applied torque T. Now to get that, what we will do is we will start with the expression for gamma max, which we have like this, say C phi over L. If you remember, so if so this is the length L, and if this length has become like this, so this is a gamma, and if this angle is phi, so C phi is equal to gamma, now gamma L, right. So from there you have this, and at the same time we also derived that tau max is equal to what, T C over the polar moment of inertia J. Okay. Now to have a feel about this expression, you can imagine that for a given shaft, if you increase the torque that you apply, obviously the maximum stress which develops on the surface, it will increase. And similarly for the given torque, if you increase the outer radius, right, so obviously the stress also will increase, because the farther you go from the center, that means on the circumference, the strain increases, and that is why the stress will increase. So that is how the tau max is proportional to both the torque and the radius. And similarly J, the polar moment of inertia, in a way, it resists, or it does not it resists the stress under a given torque. So that is how, that means the more the polar moment of inertia, so the distribution is such that polar moment of inertia is more, so that it will produce less amount of stress. Okay. So for a given torque and maximum radius. So that is how you can just think about this equation. And now to get a correlation between phi and the torque, we just have to see phi is sitting here and torque is sitting here. We have to just get the relationship between them, and we have this, right. So this gamma max is nothing but tau max over G, so which is nothing but gamma is C phi over L, and tau max over G is T C over JG. Fine. So from here, so just this C gets cancelled out, and we have phi is equal to TL over JG, right. So this is what I was talking about. So that means phi as a function of applied torque T for a given shaft. The LG, G comes from the material property, and J is a geometric property, and then so these are in a way property of the shaft, and T is the only thing which is now applied from external sources, and then phi depends on that. So this is a very important relationship which you should always keep in mind. So I'll write it again here. So phi is equal to TL over JG. Okay. And you should also keep in mind that this is the angle of twist that gets developed under the canonical condition of uniform shaft, of uniform cross section, subjected to torque T. Now, when you have here one point I want to make, you just see you can now consider this shaft as a torsional spring also, and if you just think of T over phi like a force per unit displacement, like a linear spring you have force per unit displacement, and for a torsional spring you have torque per unit angular displacement, right? So this value, if you calculate from this, it is like G over L, right? So this you can think of as a stiffness of a given shaft with polar moment of inertia J, shear modulus G and length L. Again, it's very intuitive if you think. So the polar moment of inertia, the cross section, the distribution of mass or area about the axis is J, and the more this value is, the stiffer the shaft is, right? So the more the polar moment of inertia, the stiffer the shaft is. Similarly, if you increase, if you go for a better material which has a higher shear modulus, it will become more stiff. You will require more stiff in the sense you will require more torque to produce the same amount of angular twist. And similarly, it's inversely proportional to the length, because if you increase the length, it's very intuitive, right? With the same torque you can produce higher angular twist, or you can think that if you increase the length, to produce the same angular twist you will require less amount of force. That means that it has the stiffness has decreased. So in that way you can think of this, and then you can apply all your once you calculate the stiffness of this spring, you can apply all the series parallel knowledge which you have got from your 12th standard problem solving techniques. You can use them with proper, you have to be very careful to see which springs are in series and which are in parallel, based on not from their visual appearance. Okay, if two springs are looking parallel in a visual way, it doesn't mean that the stiffnesses are connected parallelly. So you have to be very careful about that, but if you can do that properly, you can simply use the stiffness to solve the problems of multiple torsional or shafts connected to each other. And that's one. And then what I wanted to talk about, one more thing is, when you have suppose there is a shaft which is subjected to say multiple torques, you know. So then if these three segments are considered as separate units or separate shafts, because each of them is like one of our canonical problem, so you can consider them to be separate bodies, and you can calculate this, and you just have to total phi. So total phi which you have will be just algebraic sum of all these. So Ti Li over Ji Gi over I is equal to 1 to n, whatever number of shafts you have connected. And then so this tells you that you can even use different material for different portions of the shaft. This tells that the length can change. This tells you that even the area of cross section can be changed. In fact, some part can be a solid shaft, some part can be a hollow shaft, and just you have to think about its polar moment of inertia, and then you have to think under what amount of torque that particular segment is subjected to, and then use this to calculate the total the angle of twist. and this is an algebraic sum. That means in some portion it could be a rotation in this direction, and clockwise in some portion it could be a rotation in counterclockwise direction. Okay, and then that's how you sum it up. And from here, just one more thing comes to my mind, that suppose you have a, say, a varying cross section, right? So cross section is not constant, but it's varying. Now, and then suppose you just, instead of these steps, you just have a single torque applied to make the thing simple. Okay, you can do this for multiple steps, but we are just thinking that presently it's a single torque. Then what you can, how, because now this is not satisfying the conditions of our canonical problem, because the area of cross section is changing. So what you can do is you can think of a small segment somewhere, okay, of say dx length, and there, because this torque in that case will be same throughout wherever you think of, and you can think that that particular cross section at that location of x, okay, suppose this is at a distance of x from here, and so you can calculate the area of cross section there, and that is subjected to that torque. And similarly you can calculate this delta phi for that, and you can just sum them up, but now the sum will be an integration. So you can use that to calculate, because in that case, this del Li will be this delta x. Okay, so it will be something like integral of t dx over whatever. Now j is now a function of x and g, like that, right? Because j is the polar moment of inertia which changes from place to place, and that is how you can calculate the total phi. Yeah, so that's one thing. Anything else? Yeah, I think that's pretty much it. Do I miss something? Yeah. Yeah, so that's about the angle of twist which you can use to solve many problems. And in fact, one more point which I can tell, that which anyway I'll discuss in detail in the next segment, which is about, say, if there is a condition of statical indeterminate situation, okay, so where you have to use these concepts of a twist, okay, to get an additional equation, so that you will be able to solve a statically indeterminate problem. So there it will be very useful to get the conditions of angle of twist. Okay, so we will discuss them in detail, but just keep in mind that in statically indeterminate problems, the angle of twist will play a major role for solutions. So see you in the next segment.